Last year's Nobel Prize, as you know, was machine learning. And what's important in machine learning is, algorithm, software. I think those are probably the key in machine learning. But in addition to that, you need to have enormous amount of quality big data, and you need to have the GPU, HPC, which supports the training of these data in the machine. So these are all extremely important. Meanwhile, if you think about in the future, the conventional ML, which has been developing over the years, in order to improve the accuracy, we need even more data, and we need to have even more complex learning model, training model. However, high quality data, it depends on the type of data, but is expected to lack. And also in terms of the speed of the calculation and also the power consumption, we have a little bit of doubt as to the growth rate that it has been experienced over there, whether that's sustainable or not. So that is why those are the areas that we need to give more considerations as well. Of course, the progress of the quantum devices in the recent years has been incredible. And also quantum ML can be achievable or trainable with less data and even more simple model. But in terms of quantum calculation, we are able to do simulations that have been very difficult with the conventional calculation. So you will see, this high-level dynamics. So you will be able to quantum, reservoir calculation. And on the right-hand side, the green is the result of the quantum calculations. But even if there's limited training data, you are able to do relatively high accurate training as well. So these are some of the positives that have been demonstrated. Meanwhile, in terms of quantum simulation, up until now, so quantum chemistry calculations, so many have been on the molecular level, they're smaller, but now in the recent years, we have been able to do simulations on solids. So we have now beginning to see efficient simulation on a nonlinear level. So the development of algorithm and software have contributed to this. Meanwhile, using quantum computers, in order to be able to do quantum computing using quantum computers, the key is HPC or the combination with HPC. So where is HPC used? Well, for example, if you want to do quantum algorithm validation, you will be able to do that. So on a quantum circuit, or for example, error suppression or error correction, HPC. High-performing computers would be essential to do that. And before do quantum calculation, you need quantum compiler or optimization of quantum circuits. So HPC would be used as well. And in terms of I/O also, so in terms of encoding the classical data, this is the initialization state. You will also need HPC. And also, if you wanted to do communication using quantum computer, you need to read out the classical data information without really losing its original state. And this is also expected, will become useful using HPC. So in order to realize this, the supercomputers like Fugaku or Next Fugaku and GPU and FPGA and QC. I mean, this is sort of the kind of environment where we need to combine the use of these technologies seamlessly. So from 2022, we have started this project called SKY, SQAI. The greatest objective is to integrate sustainable quantum AI infrastructure by integrating quantum computers in HPC. And we worked with University of Tokyo, Riken, Keio, OISD, University of Tsukuba. And then we started with a smaller group, but now, so Tsukuba University joined more recently. And the red prints are the companies and organizations that have joined this year. So altogether, there's more than 40 organizations that's participating in this framework. And then the vision at SQAI is sustainable AI. So that AI itself, by utilizing quantum technology, will able to grow its sustainable capabilities. And as a target, you have quantum machine learning and quantum simulation technology and building a hybrid environment that allows us to do that. So this is the challenges, the actual challenges that we have been seeing. You can see 1, 2, 3, 4, 5. These what's related to the target. But in addition to that, you have quantum embedding. So the first two are related to the target, but you have quantum embedding and quantum optimization, quantum HPC as some challenges. In terms of quantum embedding, this is extremely important.
So what we have to consider is the following. Hybrid system with classical and quantum. And quantum computer does a computation result, the data that's been already attained, and how to embed that in the quantum computer. And on the other hand, within the quantum computing computer, you do the quantum computing, and how do you take the output out? So quantum embedding actually addresses that question. And we have this new tensor network. The statistical physics has been leveraged among others. And our strategy is to utilize those new technologies. So tensor network, what is that? It actually represents the state of the quantum well. It was really challenging to express this in the computer. However, the important aspects have been compressed and represented. We have MPS, tree, TN, MERA, or PEPS. There are different types of tensor network where the tensors are connected in various ways. And the so-called statistical physics problems or the ground state of the quantum mechanics can be expressed. And also deep learning can benefit from this as well. Most recently, tensor network can replace the different layers. And this is a simulation example of turbulent flow. And tensor network can actually be used as is for a simulation, as is in terms of the representation. So we are approaching this in different ways. And in our case, tensor network is combined with quantum computing. And what we're trying to do is quantum computing plus classical data structure, which is a tensor network, and also stochastic sampling technologies are used in conjunction with each other to do something new. And so we're approaching research from different angles. And in the past year or so, these are some of the quantum-oriented or related research topics. One is quantum simulation. Second is tensor network algorithms. We have developed the technology for that, and also quantum or the statistical physics has been addressed in this regard. And the third one is quantum embedding. What's been expressed or represented in tensor network, how can that be embedded in the quantum computing? And final is error mitigation. Again, this is a very useful tool for addressing all these areas. And I'd like to focus on the red text portion from here on. The first one being the embedding of the tensor network in the quantum circuit. Tensor network can take different forms. This example is a tree tensor networks. The tensors are shown in yellow, and they are connected like this. And by having this kind of connection, it can be connected in a one-dimensional fashion, which is NPS, but we can actually have this description over a longer distance. And on HPC, we have some target represented well, and we're trying to optimize that. And we will transform that TTN into a shallow quantum computer, or rather circuit. And there's a flow diagram on the bottom. This is the initial tree tensor network, but then we approximate that to simplify. And then once it's approximated, then it can be embedded. And then you actually do the reverse way. And then entanglement will be less simplified, that is, in terms of the quantum state. And you can just repeat this cycle many times. And at the end, you have several layers of quantum circuit after repetition. And that is really showing the practical quantum state of the tensor network. And BS bars and stripes, the data set, and also the ground state for many body problems have been leveraging this approach in our case. And another one is not directly related to quantum computing, however, quantum inspired, so to speak. And tensor network is to be leveraged in conjunction with conventional existing methodologies to enable something that was not possible in the past. And this is a successful case. MCMC, Markov chain, Monte Carlo method is used in different data scientist situations. And the desired distribution is actually what Markov chain Monte Carlo method addresses. However, the problem is slowness, and MCMC conversion is actually 1 over the square root, and it's actually a functional of proportional to that. However, despite this slowness, if we can actually utilize a tensor network plus the MCMC, we can accelerate this exponentially. We have the input that is put in, but against that, exponential speed up can be realized by reducing the statistical errors to the minimum. And this is the equation showing the proportion. But against that, you can actually reduce the error in an exponential fashion. So something that was not possible with Monte Carlo method, for example, negative sign problem, which is a really challenging problem to resolve. And we couldn't do any computation there, but we can do that now. And also, Monte Carlo simulating the quantum circuit itself is possible as well. And the final example is a tensor network decoder for error correction. There are different signs being proposed, for example, on the surface or stabilizer type. And where the error is occurring has to be inferred, and correction has to be made. And so we're considering this tensor network decoder to be used for this purpose. The beauty of that is the noise model in the background. The background noise will be the focus, leveraging the data as to where it's happening. The error correction success ratio can be improved. That's the benefit. However, on the other hand, noise parameters or noise model has to be in place beforehand. And what we have proposed is that you have syndrome measurements taken many, many times. And then, of course, you make corrections based on that. But based on the information that you get, then the noise model behind can also go through Bayesian inference as well in parallel. And this is a picture showing that. And there is this estimate being compared against the actual to see how accurate it was. And noise parameter, actually, it might the phase might depend on the time, but it really shows a good match. And so utilizing this approach, you have this quantum computer here. And from here, syndrome measurement is taken, and decoder is used to correct the errors. And but for quantum computing itself, you don't have to have that directly. You just do the estimation based on the data that you have, and leverage that for the sake of error correction. So for higher success ratio. So for us, quantum computers and HPC combined to make this overall system. What is needed is now we have some visibility to error-tolerant quantum computing. I/O is where the tensor network technology can be used. And so with that in mind, we're continuing with our research. So SQAI Sky project is on exhibit in our booth next door. So please pay a visit if you're interested. Thank you very much.